In my experience, the value proposition of GraphQL has largely been focused on front-end and UI development. In addition, I think there's been some hesitancy when it comes to back-end developers adopting GraphQL. I think part of this may be due to the fact that back-end developers are used to watching front-end developers constantly adopting new technologies and following the latest trends, and assuming that GraphQL is another fleeting example of that. However, in my opinion and experience, GraphQL actually has more benefit to back-end developers. That's not to say that there isn't a lot of value to be had for front-end developers and building UIs when it comes to GraphQL, but I think the value GraphQL brings to backends is highly understated. So in this series, rather than focus on the benefits GraphQL brings to front-end, I'm going to focus exclusively on the backend and how GraphQL can actually make the job easier for backend developers. I also plan to demonstrate how GraphQL really is the natural evolution of highly advanced, fully featured REST APIs, especially those with complex relations, lots of entities, and may have a variety of complex operations that can be much more difficult to define in a traditional REST API. So here we have the Spotify GraphQL API. I'm going to use this example to show you some of the reasons why I think GraphQL really does assist backend developers just as much as it does frontend, if not more. First, let me explain briefly what this query here means and why it gives us these results over here. This is just a simple example of how a GraphQL query works. You'll see over here we have this operation query artists, and we have a single argument by name, Red Hot Chili Peppers. So basically we're just querying artists by name using Red Hot Chili Peppers, pretty self-explanatory. Now, you'll also see that we have sort of these nested fields. So we have name, ID, image, which will actually be the artist itself. Then we also get the albums for that artist. The albums contain a name, ID, as well as an image. And then each album contains a list of tracks. And again, we have unique ID for the track, a name, preview URL, and then additional artists that may be featured on those tracks. So pretty simple, pretty straightforward, but there is a few levels of nesting here as we go artist, album, track, and then featured artists. So I think this is a good example for demonstrate more complex REST APIs and compare how we would design this in a REST API instead. So if you watched my Y-Elixir series, you'll notice that I'm not a big fan of open-endedness, where there's too many options or too many ways to do the same thing. And although sometimes flexibility can be good, when it comes to designing systems, especially ones that are going to be used by other teams, which is really what an API is. It's an interface between the back end and the front end. Whenever you have these contracts between different teams or departments, the more predictable and standard something can be, I think the easier it'll be. So when there's a certain degree of open-endedness or personal preference or excessive flexibility in the details of these contracts between teams, more effort is needed up front in the design stage and the negotiation stage to determine what is acceptable by both sides. So in the case of a REST API, sometimes they can be quite open-ended. There are a variety of different methods and approaches that you can take to structure this API, which I think can lead to some challenging design decisions and differences in opinions when it comes to that design. I think a great example of this open-endedness comes to resource paths. So you see over here, we have a handful of different paths that would typically be a get resource in a REST API. So this top path here is artists, which is simple enough and implies that the resource we're interested in would be an artist or a list of artists. And by passing an ID, which you'll see the ID for Red Hot Chili Peppers here, right here, In order to get the data for this specific artist here, Red Hot Chili Peppers, we would pass the artist ID as the path parameter after the artist path. So this is pretty straightforward, but it doesn't really tell us if albums are included. Now, if we wanted all albums for this artist, we would see below here, we would have artists slash the artist ID and then slash albums. And then if we wanted a specific album, we could again do artist, artist ID, album, and then album ID. Now this is fairly straightforward, but there's another way to slice this information. Rather than using path params and this sort of nested approach of resources and IDs. Instead, we could flatten it, and if, say, we only wanted to list out all of the tracks for a specific artist, we could instead just have a single top-level path being tracks. And then instead of using path params, we could use query parameters and specify the artist ID as well as the album ID, which would probably yield similar results as if we added tracks here to the end of this path. So these two could return identical results, but the path itself is drastically different. Now this approach tends to be less common and can sometimes cause issues when it comes to caching. A lot of people would argue that these query params should be reserved for actual field level filters, like if you wanted to filter by the name of a track, or if you wanted to provide sort or pagination information. However, this approach to me is a little more clear what resource you're actually requesting and tends to be more how we think about an entity in general, right? We have all tracks would be just the slash tracks, and then we're filtering all tracks by an artist ID as well as an album ID. Now, this is also a very simple example here. And the more complex our model is and the relations that we can have between various entities, the trickier designing paths can be. And in addition, this approach really doesn't tell us about what kind of information is actually going to be provided. For example, if we're querying by tracks, does it include the artist and album information? If we're querying by albums, does it include all the tracks that are in that album or the featured artists, or is it just the album meta information? Does it include the artist information, or is that implied because we already have an artist? And if we don't have the artist ID, do we have to do one query to search and find the artist ID and then another to get the albums? Or does album support a search based on its parent being artists? So although these RESTful API paths are a useful way to query resources on the server, they really create as many questions as they answer. And there's a sort of open-endedness when it comes to how much information to include. Do you include the whole kitchen sink and then let the client determine what to actually use? Or do you provide the bare minimum and require the API user to make multiple requests to get the full picture? And as a backend developer, how do you enforce some sort of consistency and predictability that will make it easier both from an implementation standpoint and a consumption standpoint? To build further on the open-endedness of REST APIs, I'd like to discuss the topic of embedded or excluded sub-objects. This is a pattern that I've seen in some REST APIs, although tends to be in more complex APIs that have lots of relations and where sometimes providing all of those relations in a single response can be a little excessive. And so therefore, clients either need to opt in to sub-objects or exclude sub-objects. And by a sub-object, I mean really a relation. So in terms of this Spotify example, a good example would be, do we include tracks when we request an album? And if we include tracks, do we also include featured artists on those tracks? Really, to what level of depth are we comfortable including by default? And do we want to provide the capability to include or exclude these sub-objects at various levels of depth? So an example of this would be if we had an artist's resource that returned exactly everything we see here, which is really the whole kitchen sink, so to speak, where we get the entire result when we request an artist resource. But in this case, we want most of that information, but we aren't interested in the featured artists for specific tracks. So in order to do that, we use the dot operator here to identify a nested sub-object that we are excluding. So we're saying we want everything in artists except for the artists on tracks on albums, which is, again, the featured artist. An alternative to that would be to have a minimal artist resource that only really provides the name, ID, and image, these top-level fields. But instead, we opt into the sub-objects. Say, in addition to the artist information, we also want albums, as well as their tracks, as well as the artists on those tracks. And unlike the exclude example, here we don't use the dot operator, so there has to be sort of some intelligence to know that artist really means albums, tracks, artists. Now, if we want to request similar sub-objects, but on a nested resource, we would have artists, the artist ID, then albums, the album ID. So now we're really just actually requesting albums rather than artists. And here we are going to include tracks and artists, being featured artists. So the assumption here, we are going to get all albums of this artist, but not necessarily the artist itself. So it begs the question, is the primary artist information embedded inside each album resource, or is the primary artist information omitted entirely, which would mean we can only get that information by making another query. So though these includes and excludes can specify sub-objects, there's no real mechanism for specifying whether to include parent information, such as the artist information for the album resource. So although this approach can give us more flexibility and help trim down requests or add additional information that we would need to get with additional requests, it again opens up just as many questions and requires the design of the API to really consider all these different use cases, which means more upfront planning and anticipation of end user needs, which may change over time and ultimately break the initial design that we intended. And to complicate things further, this only includes the sub-objects, not individual fields of those sub-objects. So if some of these sub-objects are highly complex and have a variety of fields, we only need one or two of those fields, maybe even just like an ID and a name. That means we're either overfetching significantly, or we would need some sort of mechanism to specify fields of these sub-objects as well, which really is just not feasible in a REST API. So now it becomes more of a judgment as far as how much of each sub-object to include by default for any particular resource. And for a backend developer that doesn't really know all the use cases, this introduces a tremendous amount of open-endedness that is probably going to require a great deal of communication with the end users that will ultimately be consuming the API. At this point, there's a great deal of questions already about how to design a REST API for even a simple domain such as this. It's not hard to imagine how much more complex this could be if you have, instead of a handful of entities with a straightforward hierarchical relationship, you have dozens of entities with a variety of different relationships. And at this point, we've really only covered what we're requesting and haven't even considered more advanced features such as filtering or sorting or pagination. As mentioned before, it's not as common to see this approach where you're specifying the relationships as query parameters. Relationships, especially nested relationships, tend to follow this path-based approach rather than use query parameters to filter specific resources based on their relations. Query params are typically reserved for actual filtering, not by relations, but by, say, individual fields, or for sorting and pagination. Some examples here are filtering tracks based on the name of the track. And although it's easy enough to specify fields for filters on a specific resource, sometimes we need to be able to filter based on a parent or a child. In this example, we're interested in all tracks where the artist is the Red Hot Chili Peppers and the album would be By the Way. Now in the database, it's highly likely that the actual artist name and the album name would not be included in the track table itself. Instead, the track would simply have an artist ID that would point to the artist and an album ID that would point to the album, which means in order to filter on a parent of a resource, where album is a parent of track and artist is a parent of album, we would likely need to use joins in our database query. So although we're only interested in the tracks resource here, we actually do need to join with the albums table as well as the artists table and then search based on attributes in those tables. This makes this query much more expensive and complex than if we were simply filtering by the track name or some information about the track itself. The same applies when it comes to filtering by a child of a resource. For example, if we wanted a list of all artists that have had Red Hot Chili Peppers as a featured artist on any of their tracks, we would need to perform a similar join with all artists, all of their albums, all of their tracks, and then all of the featured artists for those tracks, which would be much more practical to do the other way around, where we instead search by the featured artist table where we see Red Hot Chili Peppers, but then again we need to join now up that hierarchy. So we would first query the featured artists table in the database, filter that by Red Hot Chili Peppers, and then join that with the track, the album, and then finally the artist. And then the only thing we're actually interested in returning is the list of artists that meet that criteria. And now we could have the same query, but instead of returning a list of artists, we're returning the list of tracks, which is better because it's two levels of joins we don't need to include in the hierarchy, but is a separate query altogether that will either need to be written by hand or use some layer of abstraction that can automatically infer that we need to do these joins and do that automatically rather than requiring an explicit query to be written. Now, in addition to these filtering parameters, we also have query params that are typically used for pagination, where we'll get a list of tracks, but we're going to limit it to 10 at a time, and we'll paginate those results, and that helps keep that main list down. Or we can sort tracks by, say, the name of the track alphabetically, and we can sort that either ascending or descending. And sometimes we can even have multiple sorts where we'd have sort name and then artist, or we could say year. So as we proceed in adding functionality to our REST API, it should be apparent that the complexity increases dramatically with the use cases, while also not being entirely clear the best way to implement these sorts of features. And again, as the domain becomes increasingly complex with additional entities or more complex relations, we quickly hit limitations in the REST API and need to spend more and more time upfront designing this API rather than implementing it. The alternative is to support minimal features on these resources. So we wouldn't be able to sort by parents or children or specify which sub-objects we want to include or exclude and keep our nesting to a minimum. But the trade-off there is that clients may need to make multiple requests in order to get all the information they need, which eventually leads to 5 or 6 requests per page load instead of 1 or 2. So there needs to be some degree of balance introduced in the design where you hit that sweet spot between functionality and complexity and minimizing the amount of API requests needed to be made by a specific client. So let's just assume for a moment that you've actually found the perfect balance between all these considerations. got just the right amount of filtering, you know exactly what to include with each resource, how to specify sub-objects if necessary, and overall feel really good about the design that you've chosen for your REST API. Although that's a great situation to be in, now you have the added problem of documenting that perfect design. Luckily, there are good tools out there to document your REST API. The last time I needed to document a REST API, Swagger was the best choice and provides some great tools to do so. But anyone that has had to document a REST API using Swagger or some similar approach will know how tedious of a process that can be, especially if you have a complex domain. You need to list every single path and operation. You need to create representations of every single model or entity in your system. You need to specify every query param and path param that exists in the API. You potentially want to provide sample requests and request bodies, especially for APIs that are responsible for creating or updating resources. You also have to accommodate for error cases and error objects that may be returned from the API, including the various status codes that may be associated with those errors. You also have to account for fields that may be nullable and may or may not contain a value. And to make nullable fields even more confusing, you may also return what would be considered empty values, such as empty strings, or maybe a 0 for numbers, or an empty object, or an empty list. So you may need a distinction between these return values as well. And all of this time and effort you spend on documenting this doesn't directly benefit the code or your system. It's merely documentation for your clients. That also means it'll need to be updated every time you make changes to your API. And eventually you'll have new versions of your API, which will require doing this process over again while still keeping the documentation for the older versions. And if that isn't enough work for you, you still may need to manually validate all of this information on the server, especially for request bodies. Do you want to support the ability for a client to send a numeric value as a string, or are you going to manually validate that on the server and ensure that only a number value is provided in that request body? And what if you have a range? What if the client is only able to specify a numeric range between 50 and 100? Not only would you need to provide that in the documentation, but you would also want to validate that on the server prior to persisting that value to the database. As you can see, there's a tremendous amount of work and effort that goes into accurately documenting a REST API. And it is not a one and done. It'll need to be actively maintained as you make changes to your API. Considering the amount of code abstractions and tools we have available for us when creating APIs, you may actually find yourself spending more time and effort documenting and validating your API requests and responses than you do actually building that API. In addition, it's extremely tedious and error-prone work, and something that your developers are going to be very reluctant to do regularly. I think for this reason alone, GraphQL makes more sense than REST. Unless you have the most basic of domains, the fact that GraphQL will automatically document and validate your objects means that all of this manual work of documenting your API is no longer relevant. And simply by virtue of building your API, you are documenting it and validating it. And because these GraphQL schemas are standardized and follow a specific spec, you have a variety of different tools to inspect your schema, as you'll see here. If we click into our top level root query, we'll see that we have a couple operations, really the most relevant one being query artists, which is what we use here. And we'll see that query artists operation returns a list of artists and accepts a single argument, which is a string by name, and provides an example, which is Red Hot Chili Peppers. Now, if we click artist, we'll see that we have automatically documented the fields for an artist, which include name, which is a string, and a required string, thus the exclamation point at the end of string. We'll also see that we have an ID field, an image field, which optionally is a string, So this could actually provide a null value as well. And then we also have a list of albums that we can actually limit by specifying a limit argument to. So if we went down here, we use limit, we could limit by 5, for example. Now we'll see that albums returns a list of album, and we can thus click into album. And we have sort of a similar layout to artist and a list of sub-objects being track. And again, we can click into track. See, we have, again, name, which is required field, and then the optional preview URL, and then a list of featured artists, which then returns a list of artists, which then actually brings us back to the top level artists that we started with. Now, the beauty of GraphQL is that this documentation is provided automatically simply by building our API. By defining our types in our code, it will automatically generate this documentation. And in addition, there's a validation step that occurs when a query comes into a GraphQL server that will ensure that these types that are specified actually match the return value of the response or the inputs that are provided if we are, say, creating an object. So that means all of that work for documenting and validating a REST API comes out of the box with the GraphQL API, and is done so in a way that really makes it effortless for the developer. And because every GraphQL API follows this standard spec, all APIs are going to follow this same sort of structure. So this documentation explorer will work the exact same way for any GraphQL API out there. So even if you ignore everything that is discussed in this series, you are a backend developer and you know that you need to document your API. Do yourself a favor and just use GraphQL and let it do it for you, because maintaining that API documentation can be a nightmare and is likely not how you're going to want to spend your time. So there are a few other things I'd like to mention before we move on. At this point, the benefits of GraphQL from a design, documentation, and validation standpoint should be clear, but there are a few other advantages I'd like to discuss. First off, we've only really compared GraphQL to REST. And although REST tends to be the most common way to build an API, there are other options out there. Prior to REST, remote procedure calls were pretty common. And really, I'd say GraphQL is more like RPC, or remote procedure calls, than it is REST. You're really only using a single endpoint, and then on that endpoint, you're calling various functions. And even from the syntax of a GraphQL operation, it looks like a function where you have the function name and then some arguments that you provide. Now, RPC tends to be a much more simplified version of GraphQL. It really is just about calling a remote procedure and returning the results. GraphQL gives us the additional benefits, obviously, of the documentation and validation, but also specifying which fields and what data to return, and allows us even to nest our remote procedure calls, where we could have additional filtering or searching on really an infinite level of depth beneath that top level object. So as you see here, we have our top level remote procedure call, querying artists, but then on albums, we specify an argument as well. So in a lot of ways, I like to consider GraphQL to be sort of like an RPC 2.0 that builds on that sort of mentality of calling or executing a procedure on the server and returning the results, but doing it with far more features and capabilities than traditional RPC. Another nice feature of GraphQL is that it can act as sort of an API gateway, where it is responsible for being the single endpoint that your clients use to query data, but behind the scenes can be orchestrating calls to a variety of different microservices, or making database calls, or even querying third-party APIs. Now, I have had the privilege of working on a REST-based API gateway, which now introduces even more complication when it comes to validating requests and documenting them. Because not only does each individual microservice or service that the gateway is consuming needs to be documented, but now the gateway itself needs to be documented and potentially need to validate requests prior to hitting the individual services. So even if you're in a microservice architecture or service-oriented architecture, and it's not feasible to re-implement all of your RESTful services into GraphQL, you could start by using GraphQL as the gateway itself and using the GraphQL resolvers to orchestrate requests to a variety of different services while providing that unified API and documentation that your clients will benefit from. Later in the series, we'll get deeper into gateways as well as schema stitching and federation, which is how you can use GraphQL in a microservice architecture. But for now, I just wanted to touch on the benefits that GraphQL can provide as a gateway over a REST-based gateway. And finally, something that I haven't really seen used in practice, but I think can be a tremendous benefit not only to engineers, but the business itself, is the ability for GraphQL to be used as the language between the business and engineering. A lot of times it could be quite challenging for product owners or business stakeholders to communicate to engineering the requirements of a product. And the GraphQL SDL is simple enough for business stakeholders to communicate this in GraphQL, simplifying the specification process for engineering and introducing a collaborative way of building out your domain. As you see here, we have a very simple GraphQL schema. And this could live as a file in a GitHub repo that both engineering and product has access to and can collaborate on. So you could quite literally define your entire API and business language using this SDL and then implement accordingly. You could even use this GraphQL file itself to build out your schema and then only need to define the actual resolvers, or you could simply use it as documentation and specification and then build your API accordingly. So in this simple example, we have two types. We have a post type and a blog type. We'll see that every post has an ID as a required string, a title as a required string, a date it was published, the amount of likes, which would be an integer with a default value of 0, and then a relation to the blog type. And then for blog, we have similar fields, ID, name, and description, which is optional, and then a relation back to posts. Now this is an extremely simple example of a GraphQL schema, but as you see, this is really something that is simple to understand even if you don't have an engineering background. And sure, you might have to understand the differences between a string and an integer and whether something's required or not, but for someone who's a subject matter expert in the industry and really knows the ins and outs of the domain is probably going to be better at defining this than engineering, where they may lack the industry knowledge and experience. But really, engineering only needs to know this. So GraphQL as a language is easy enough for product and business people to understand and work with, but descriptive enough for engineerings to base their development off of. And again, using a GitHub repo and some static GraphQL files, both engineering and product can work and iterate on the GraphQL spec of the organization and define the domain using GraphQL schema and minimize the miscommunications between the two sides. Plus, the more experienced stakeholders are in GraphQL, the better they'll be able to actually use the GraphQL API via the Documentation Explorer and actually query the data themselves. So GraphQL can serve as a great communication language between the business and engineering. So to summarize this section of the series, we've covered some of the open-endedness of REST APIs when it comes to designing paths and query params and path params, sub-objects and field selection, filtering, pagination, sorting, all of these things that really require some upfront planning and design. And although it can be fairly standard across the industry, your specific domain or use cases can easily break outside of the norm and lead to API design that requires some ingenuity in order to work effectively. And even if the design considerations of your API are pretty straightforward and you're not really concerned about those types of problems, you'll still need to document those API endpoints and validate them, which can be some of the most tedious and error-prone tasks you do as a developer, and not particularly pleasant as well. And if you have some sort of API gateway, you're now actually doubling that amount of work, because now each individual service needs to be documented as well as the gateway itself. And finally, the benefits of using GraphQL as a communication language between the business, product stakeholders, and engineering can be an invaluable tool and help bridge the gap between product specifications and engineering specifications. In the next section, we'll go through some of the extension points of GraphQL and where we can hook into certain points of the GraphQL execution to generalize behavior or perform middleware-esque tasks that help simplify our code and speed up development.